Welcome to coming into Module 2 for our Maps 204 class. So Module 2 is all about scales, and so we will be doing some math with this, and we're going to be doing some measuring, and so this is where you're going to need maps. We will be doing things with paper maps, just because I find that it's the easiest way to conceptualize what's going on. And so that and really this module um, is the basis of kind of going forward with any kind of mapping, any kind of drafting, and definitely when it comes to being able to take the real world and be able to represent it in a proper measurable format, scales are so essential. So we're going to be going through everything from like really what is it all the way up to the actual math that goes into it. So this module is not a very big module, but it is a very important one. So my first objective is to compare the different types of scales. So normally here we have 4 examples of types of scales. So we have something called a representative fraction. So the representative fraction doesn't necessarily need to be the same unit. It just has a little division sign in it. It can be the same unit if you want it to be. So if I want to say 1 centimeter over 500 or 50,000 centimeters, then we have a representative fraction as well. So you can also use different kinds of units. So we can use the imperial system with the metric, just as long as that division sign is an actual division sign, not a ratio sign. Then we also have word scales, and these word scales are where it's actually written out. You're going to see word scales on something we call a township plat, and it'll say, 1 inch is like so many chains. So this statement is written out. Usually it is going between different kinds of units, and it is oftentimes definitely between the different kinds of I guess, sorry, like imperial to metric or 2 different kinds of metric, go between there. The scale bar itself is a visual representation. Now, this is often a illusion, I guess, if you want to say that. It really throws off people. So the whole idea behind a scale bar is to give a general view as to how far away something is. So you can use a measuring tool or whatever and measure it. But this is not a mathematical scale. Okay, so this is merely just to give you that kind of overall view as to when you use a ruler. You can't say that, oh, it is 200 miles. The scale is 200 miles, because that doesn't make any sense. So this is really just for that visualization. Then we have the unitless ratio. So nowadays you're going to see pretty much everything have a unitless ratio. If you go into Google Earth or Google Maps, you do see a scale bar. Again, that is for that quick, like general, how far away is that? If I actually have to do math and I have to like do calculations with it, I'm going to use a unitless ratio. The nice thing about the unitless ratio is that I can use any unit. It just has to be the same unit between the 1 and the number after the colon. So if I say, looking at this particular unitless ratio, if I say 1 centimeter is 20,000 centimeters, then I don't need to have the centimeters on there because it means the same thing. Now, if I go to the exact same map with inches and I want to use inches to measure, 1 inch is still equal to 20,000 inches on the ground. Now that comes down to the actual like definition of the map, right? So or map scales. So I haven't actually defined that, and I just kind of jumped into that. So let's make a really quick definition of what a map scale is. So this 1 that is at the beginning of the ratios, or here, it's always going to be a 1. Very rarely would you ever see any other number than 1. So this 1 refers to the map. So whatever I measure on the map. The last half of it, whether it be in the word scale representative fraction or in the unitless ratio, this last one is the representation on the ground. So when we try to define what a scale is, we're basically stating it is the reduction in measurement from the Earth's surface to a piece of paper or other medium, which is like the digital world, so that we can represent and generalize our Earth's surface. So that's what this 1 represents. Is the 1 is that map, the number after is the real world. So that's the definition. Now here we have the size of the scale. So this is really a relative statement. So it's really hard to say, you know, there's a certain number that cuts between small, medium, and large. But just understanding when I state that I'm dealing with a small scale or I'm dealing with a large scale, if I say a small scale map or a large scale map, what does that actually mean? Now, the thing with this is that it can get kind of confusing because small scale, everyone thinks it's like a small little area. That's actually the wrong way of thinking about it. A small scale covers a very large footprint on the ground. So which means that I have very small details, right? When everything looks like really zoomed out, so you can like zoom in, zoom out. As you zoom out, and let's say you're getting further and further away, as if you were going to be looking from a satellite or or even further, though that's zooming out, the details are very small, but it is considered a small scale. So the bottom number, the larger number in the ratio, is going to be quite large. Saying that, if I calculate the ratio, so if I go 1 divided by whatever the number is, it gives me a really small value. What number is that? It really depends on what you're working with. If you're a land surveyor, oftentimes the difference between a small scale and a large scale is relatively small. In mapping, a small scale and a large scale are very different numbers, but there's no real cutoff line. So to compare the large scale, we have a very small footprint on the ground when I have a large scale. So we actually have very large details. So if we zoom in to the scale, so zoom into the map, now we have a large scale. So you'll see that in the Google Earth, as you move in, you're going to see the scale actually goes down, the number after the colon actually decreases. So the bottom number of the ratio is small. So if I actually calculate it through, it means that the ratio gives a larger number. So 1 divided by 500, for example. So an example of a small scale might be 1 to 250,000. An example of a large scale might be 1 to 500. So these are really important for the size of paper. So you're going to definitely see paper sizing coming up in assignments or in exams. You don't have to memorize that stuff. I find it ridiculous that you have to memorize that when you can look it up. It's really easy. But if, for example, what's really important between these two is, let's say I change my paper size. Like, oh, you know what, I'm not going to put it on an 11 by 17. I'm going to put it on an 8.5 by 11. If I need to maintain the scale, I'm actually going to move to I need to go to a smaller scale, and I'm not going to be able to maintain it that way, if that's not what I mean. So if I were to maintain the scale, a large scale map, if I go from a large piece of paper and I make it to a smaller piece of paper, I actually lose part of the map. It falls off the paper. So if I have to do that, I have to move. If I have to move to a smaller paper, I'm going to move to a smaller scale. So you can't increase your scale, because if you increase your scale size, it actually is going to fall off the paper. If you reduce the scale size, it means you're making it smaller, you're zooming out, so you're kind of making it smaller and smaller, and therefore it's going to fit on the paper. Now, this one here, it says, let's say that I have 2 different papers. I have the same area, 2 different papers, they both fit on the paper just fine. And if I change that paper size, then this really doesn't apply, right? So it's not really a case of like the the scale that again going back to that number, right? So if I'm going to say like what is the cutoff between small and large, it's really hard to say, yeah, well these ones are this one's a large scale and this is a small scale based on the paper size. There's no number. It's like, oh, at 1 to 10,000, that's going to be my new scale size. So what I mean here with this statement, so it says it's important to remember that the above table describes scales on the same size of paper. Okay, so that's really, when I use one size of paper, I can say these are the different types of scales. If the paper size changes between the two scales, then these relative comparative statements will not apply. I can't compare two different sizes of paper. Okay, so that's just really what it is, because otherwise I can't say that, oh, on the 8.5 by 11, that is definitely a small scale, and if I put it on 11 by 17, therefore it is a large scale. You can't really say that. It doesn't apply. Okay. So moving on to the next stage. Next objective is calculating the scale ratios. So really the rest of this objective, or the rest of this module, is the calculations. So here we have a scale ratio formula. So the top here we have 1 over s. Now I write it out this way. I'm going to be teaching you in one way and one way only, because I'm going to avoid any kind of confusion. That's my goal. So if you know of other ways to do this and you don't want to do it this way, that's okay. I am fine with that. Again, I'm just trying to stick to the same style of teaching that I started with the unit conversions, and I'm going to keep going through with that same style. So if you do want to do it differently, there's many other ways of doing this. It's still the same formula though. So to define this, 1 over s, this is my scale. Now, it's written as a representative fraction in this mathematical formula, but it does become a unitless ratio. So if I put the 1 and then I have the colon, which would be where the line is, and then I have s, which is the scale number. So we're often, in this case, we're trying to solve for s, which would be the scale number. So, but I want you to remember that when I ask for a scale, you give me 1 colon s, whatever the s number is. Okay, so that 1 colon is really important, unless, because you've read the instructions of every single question, if it says do not add the 1 colon, it's because it's been a formula that I've put into the computer, so it won't accept that. So just make sure you read the question very closely. Here's the distance on the map. So on the top of the formula, on the other side of the equal sign, we have distance on the map, and then we divide by distance on the ground. So I refer to this as dm. So at the top of the numerator, it is referred to as dm for distance on map, and on the bottom, I represent it as dg, which is distance on the ground. So here's an example, just jumping right into some examples. So if you were to measure a distance on the ground to be 526 meters, and the same distance measures 26.3 centimeters on the map, what is the scale ratio? So I have my formula, 1 over s equals dm over dg. And that becomes 1 over s equals 26.3 centimeters divided by 526 meters. I have to make sure that my units are the same because I'm dealing with a unitless ratio. So I convert the the denominator into centimeters. So I have 26.3 centimeters divided by 52,600 centimeters. Then I'm going to cross multiply and divide. So I'm going to take my 1, or sorry, I could do it this way. I can go 52,600, multiply it by 1, which is at the top because I cross multiply, and then I divide by 26.3. So that gives me an answer of 2,000. I do not give, if I'm asked for a full scale ratio, I always give the 1 colon, because otherwise it's just a number. I didn't ask for the scale number, I asked for the scale ratio. So really be careful about that terminology. So here, write your answer with the 1 colon. So answer is 1 colon 2000, which we would say in English 1 to 2000. And that's the scale. So that's how you calculate that. Now if we go into the next example here, is another one. So if you were to measure a distance on the ground to be 1,931.05 meters, and the same distance measures 34.2 centimeters on the map, what is the scale ratio? So we have 1 over s equals dm over dg, and that gives me 1 over s equals 30, oh, I have an error there. I will be fixing that. 32.2 centimeters over 1,931.05 meters equals 32,000, or sorry, which putting it into the same unit, I have 32.2 centimeters divided by 193,105 centimeters. Now I cross multiply and divide again, so I have my 193,105 centimeters, multiply it by 100 for the cross multiplication, and then I divide by 32.2. That gives me 5,997.05. Wait, we have decimals. Have you ever seen a scale with decimals? No, right? So we need to round. Now, with rounding, I've taught a little bit about that. I need to emphasize that this is different. Scales are different. So I need to be very clear about this. So rounding must always be up, no matter what. If there's a decimal, you round up. Okay. The reason being, we need to make it a smaller scale, not a larger one, right? So we talked about that when I was just in the last objective, when I was talking about the difference between small and large scales. If you think about it, if you are going to zoom into your map falls off the paper. If you zoom out, the map stays on the paper. So we need the number, the denominator, to actually go up in value. So we always, always, always round up in scale ratios, no matter how small the decimal is. Okay, so here we have 1 to 5,997.05. That becomes 1,500, or 1 to 5,998 as my answer. Even though this is 0.5, that would normally round down to 0.997 in normal math. In scales, it's not normal math. We have to round up because we don't want it to fall off the paper. So in this class, we will not be rounding to the next zero. Okay, so don't go to zeros, please. So just take your numbers and just round it to the nearest one. Okay, so I know that in most drafting situations and a lot of mapping situations, they're going to ask you to put it to the closest, like 1,000 or 100 or even 10,000. It's a very complicated situation, and different companies have different standards. So I just want you to get into the habit of rounding up up to the 1, not to the zeros. Okay, so that's just a very important note in this case. But you always round up, because if you don't round up, then it's an incorrect answer. All right, so moving into Objective 2.3, we're going to be plotting maps and we're going to be plotting plans to scale. Now, because we are doing this online and you don't have access to a plotter, we will not be doing this. So I'm going to describe it. So when you are plotting, you need to ensure you choose the correct paper size to start with, right? So if you have a paper size that's too small, you're going to have part of that paper or part of the map fall off. And if you have too large, you're just wasting paper. Save a tree. Because then you got to sit there and cut all the paper off and it adds extra work. So if you just choose the right paper size, then you're good, right? So that's number 1. Number 2, you also need to ensure any options that might adjust the scale of the map are turned off. So most like PDF, when you go to print, even TIFFs, it'll say fit to page, it'll say scale a certain number, or you can adjust that, or it might say there's a whole bunch of different options depending on the software that you use. Any of those options, turn them off. You don't want to fit to page. You don't want to scale it to a certain amount. You don't want to go page width. You don't want to do any of that stuff. You want to print actual size. So well, pretty much every software that deals with printing will have actual size or real size or no scale. So make sure that you use that option. Do not allow it to fit to page because you will end up with a different size. So why do we do this? Because if you change the printing size, the map will show up as a different scale than what it was intended to be. And if you hand that off to an engineer, they're not going to be very, very unhappy with you because the values that they're using do not match. And then they'll end up with incorrect values, and perhaps you just ended up buying an extra 10 loads of dirt, which is a lot of money. So I do suggest making sure to always double check every time you need to print something in paper or even print it to PDF, because that is another error that happens. And PDFs that can also be scaled or fit to page. And because everything is becoming more and more digital and less paper, it is really important to watch that and ensure that you're being careful about that. So that's really all for that objective. If we were in the classroom, I would get you guys to plot a map or two, and then we'd be using that one for the rest of the semester. Oh. All right, so objective 2.4 is calculating distance and areas using scales. So here we always use the same formula. As soon as you use scale, you are doing the exact same thing with the exact same ratio, except that you're just using different numbers. So the methodology is pretty much the same, and it's just solving for another value. So if we're solving for the distance on the ground, we need to solve for dg, right? We talked about that. So as an example, you are using a 1 to 10,000 map and measure the distance between 2 points to be 12.6 centimeters apart on the map. So you actually use a ruler on there. Note that I don't give you a whole bunch of decimals after the after the first decimal place for centimeters. The reason being that I do that is because how accurate is or even how precise is your ruler? So you might say, well, you know what, I can still read that it's only like a partial component of a millimeter, but is your ruler that accurate? And I even asked that with Google Earth. Is it really that accurate? So I'm only going to ever give you 2 millimeters because the accuracy of rulers is actually quite low. If we were working in groups, you would actually find that everybody gets slightly different answers. And that's because the calibration of rulers is not necessarily totally standard. So yeah, so just keep that in mind. The different materials of your ruler, depending on the temperature, is going to adjust the sizing, everything like that. So keep that in mind. All right, so going with the numbers, so we have 1 over s equals dm over dg. And so therefore 1 over s is actually equal to 1 over 10,000, just like it gives in the question. My measurement is 12.6 centimeters. Now I need to cross multiply and divide. So I take my 10,000, I multiply it by 12.6 centimeters, and I divide by 1. Then I get my dg, which is my 126,000 centimeters, or putting it into meters, which makes more sense. We're going to go with 1,260 meters. Yeah. You'll note that in some of my PowerPoints that I give some example places where I got it. And so these are, you can always check for any of these examples or links that I've provided you. All right, so scale area calculation. So if we continue on, area is a value squared. So that it means it's the same for the scale. So if you want to work with a single calculation, you can go 1 over s squared, so both 1 is squared and s is squared, equals area on the map over area on the ground. Now because, again, remember area is length times width or base times height or any of those, I have two values that are getting squared. So it'd be like a centimeter squared, a meter squared. So this area value, you're not actually squaring the area, you're giving the actual area value, but it's that length. So AM is the area on the map, AG is the area on the ground. if you can break it up into a rectangular shape or a triangular shape or something that is very simple, calculate length and width separately. I am not going to give you an example of this because it is very confusing with scale area. So there are actual maps called equal area, which you can use scale values, like area scale values, and they actually make sense. Those are usually for like something called a thematic map, and so therefore they're looking at like political boundaries and voters and maybe showing the number of cows that are sold in an agricultural area. So the scale for the area is not necessarily that important, where it's more showing it a visual representation more accurately. But if you do have to calculate scales when you have area measurements, break it up into the rectangular shape and do the length and width separately. So don't do them all together because otherwise it just becomes one big large mess. So that's just my suggestion. You may find that if you are doing it separately, you might find like scale values are different between length and width, which is very normal because of the fact that we have convergence with the Earth being round. It all comes together at the north, so you might find that the different values are different. So just keep in mind. So Objective 2.4, apply scale calculations to use between maps. This is actually a key objective that you're going to see again in photogrammetry, because in photogrammetry we don't have a scale on the photo and we have to figure it out. But oftentimes, let's say you get a thematic map, somebody hands you a thematic map and you're like, I wonder how big this is or how far away this is. There is no scale attached to it. A good example is the SAIT campus map. So if you go online, you download the campus map and you take a look at it, there's no scale on there. So how can you actually figure out the scale of the map so that you can actually calculate the distances? So there's a few ways of doing this, but if you are, for example, not on campus and you need to do this and you can't get access to the ground, you need to use another map in order to do this. So you just really this map that I'm talking about, this other map, it has to have a scale. It doesn't need to be the same scale as the other one, but it just has to have a scale, and it has to cover the same area. Okay, so don't like, oh, it only covers a little part, so I'm just going to use it anyways. You need to make sure that it covers the full area. So another thing that can happen over time, things can change. This is why we have to calculate between maps. Rivers move, infrastructure has changed, forests are burning, etc. Any old maps that you have can help to create a new map of the area. So again, calculating between maps does still happen. It's more and more digital now, but it's really essential in like remote sensing. We do a lot of this. So we get to use the scale formula twice when we get to do this. So we have 1 over S1, which is the first map, equals dm1 over dg. And then we also have 1 over S2, which is the second map, and equals dm2 over dg. So dm and d2 are the measurement, dm1 and dm2 are the measurements on each map. dm1 is usually the map with the recorded scale, so you know the scale on that map. And then S1 is the scale value of the first map, S2 is the scale value we're trying to calculate. dg is the same. So I really want to emphasize that because, for example, I have two maps that have two different scales. The measurement on the maps are different. Does that mean that depending on the map I am looking at, the ground changes? That would be pretty crazy. Like, could you imagine that? Somebody's looking at a map and all of a sudden the earth changes in front of you because they're looking at a map and making a calculation. Like, and also it like shrinks and it gets bigger and shrinks and you're like trying to get somewhere and you keep like, it's almost like this weird accordion that you're on as you're walking down the street. It doesn't happen, right? So that would be quite the world that we live in if that was the case. So, but DG always stays the same. If you measure the same location, if I measure like from campus center to let's say the Thomas Riley or 16th Avenue, if I do that on the same map, and then I go to another map that has a scale and I look at that and I measure it and it's a different value on the map because it's a different scale, it doesn't mean that it suddenly got bigger or smaller to walk from Campus Center to 16th Avenue. It's always going to be the same. But you're going to measure the same between the same 2 points on both maps. So DM1 and DM2 are the same 2 points, the distance between the same 2 points on both maps, but DG does not change. It has to stay the same. Okay. All right, so you are trying to determine the scale of a new thematic map that you created and are trying to fit it onto an 8.5 inch by 11 inch paper. Using a 1 to 2500 map, you measure a distance to be 14.9 centimeters. So this is my known map. The same distance on your new map is measured to be 22.6 centimeters. So when I say same distance, I'm referring to the distance between the same 2 points. What is the scale of your thematic map? So coming down here, we have 1 over S1 equals DM1 over DG. So I have my 1 to 2500 equals 14.9 centimeters divided by DG. So we're calculating DG. We need to cross multiply and divide. DG times, or sorry, not DG, 2500 times 14.9 divide by 1. And I get my 37,250 centimeters on the ground. So that is going to stay the same between both values. So it doesn't change. So I'm going to use this value in my my formula for S2. So I have 1 over S2 equals DM2 over DG. So 1 over S2 equals 22.6 centimeters, and I have 37,250 centimeters. So I cross multiply, so I have 37,250 centimeters, multiply by 1, divide by 22.6, and then I get a scale value of 1,648.23. So I add in that 1 colon because that is part of the answer, that is part of the scale. So my answer gets rounded up all the time. So my answer is 1 to 1,649. And that's my answer for that question. That is the scale of my thematic map. So last but not least, here we have our apply scale calculations to use between map and ground measurements. So we're still using the same formula. So I'm using an example here. This one is really to determine your paper size. That's why we would use this. So you have this map, and I'm just jumping into an example right here. Your map is 1 to 9,000, and you measure a distance on the ground to be 811.3 meters. What is the distance on the map? So again, checking paper sizes, trying to figure out what would work. We have 1 over S equals DM over DG. So 1 over 9,000 equals DM, which is distance on the map, over 811.3 meters. So I cross multiply and divide. So I have 811.3 meters multiplied by 1, divide by 9,000. And I end up getting 0.09 meters or 9 centimeters. So that means, depending on the direction this is, I either can use an 8.5 by 11 map, if that is the full distance, or sorry, the 8.5 by 11 paper, not map, 8.5 by 11 paper, and that 8.5 by 11 is in inches, remember, so we have that unit conversion. So this could really fit on pretty much any paper. So I would hope that if your map has to be a 1 to 9,000, and this is only just a tiny part of the map. So again, suggesting that you go a little bit further out and do more along those ways. All right. So in conclusion, some of the key points. First of all, scale values do not have decimals. There's no decimals. Never, never, never write a decimal for a scale. When writing a scale ratio, always use the 1 colon in front, unless otherwise stated. So again, read the instructions. As we go back to Module 1, read the instructions. Again, it just depends on the style of online question. If it was on an exam and I had a short answer and you didn't give me the 1:, then it's wrong because all you did was give me a number, you did not give me a ratio. All right, then always round the scale up to get a smaller scale. So that denominator needs to go larger so that you can get a smaller scale. Always round up. Proper maps should always have a scale ratio and a scale bar on them. Both of those are important. Just as a really quick reference, you have, oh, okay, this is how far that is, and then, okay, now I can do the math with it. Then the equation can be used in the following equation can be used in all situations that have to do with the scale. So 1/s equals dm over dg. They will become more complicated in the future, but this is the stepping stone to begin with. So that is scales, and if you have any questions, feel free to use the open forum, and I will be seeing you guys again or talking with you guys again, I guess, with the Module 3.